Thank you for attending my talk on a universal particle structure that gives all particles their properties. This is a brief presentation on particle physics. It uses only known particles, forces, and physical constants in three space dimensions and time. It describes the physics involved and then uses what I call the simplest possible maths to accurately determine the magnitude of the physical effect that they generate. Now, I suggest that to be complete, a particle physics theory should also show how their structures and properties combine to give the world we see around us. So, but before I start, just to show one example of how this works, I refer you to this paper, which you can view at either of these addresses. And the physical principle that Einstein used was that he applied Newton's gravity to photons that had mass. And that was a paper he wrote in 1911. In 1916, in his foundations paper, he went through and developed a whole lot of field equations. And people who solved those field equations believed that they predict black holes from them. Einstein didn't believe in them. And when you go through his mathematics carefully, you will find that in order to derive black holes, they needed to make three mass errors and not understand some simple physics. For example, Einstein derived G11 equals minus 1 plus alpha over r, which he then approximated to minus 1 over alpha minus r, and that is the solution, that is the equation used in the so-called exact solution. At the same time, he derived G44 equals 1 over 1 plus alpha over r, because they are the negative inverses of each other. He approximated that to 1 minus alpha over r, and that is what is used in these so-called exact solutions. When you go through it all, and you can reduce, well, get four metrics out of it. Newton's metric, Gm over r squared. The exact solutions to Einstein's field equations become Gm over 1 plus alpha over r times r squared. Black holes, one is called 1 minus alpha over r. The exact solution to his the physics he used is I call it Gz for redshift, Gm over r squared e to the alpha over r. That actually directly predicts the structure, the torus-like structure observed from the center of galaxies. But the main thing that comes out of this, or one thing comes out of this, to understand Einstein's gravity, what Newton called r squared becomes, under Einstein's gravity, r times 1 plus z. So what Newton called r becomes r times 1 plus z, where z is the redshift. So this equation, I think, is relatively easy to use. It's not much more difficult to use than this one, which makes understanding Einstein's gravity considerably simpler. Now, if you have a look at both of these equations, they show that Einstein's gravity is weaker than Newton's inverse square law. I mean, weaker gravity means that Mercury orbits a little further away than it otherwise should from the sun. It's also attracted by a weaker gravity, so it takes longer to return to its perihelion position, and therefore it returns to it a little bit later in each orbit, and that is why Mercury's orbit precesses. Now, gravity being weaker than inverse square, causing a planet's orbit to precess, was worked out by Newton in 1687. This weaker than gravity is entirely consistent with that. But I'm just using that as an example to show that if you know the physical principles, you can in fact get the maths much easier and get rid of any errors that have the possibility of eliminating errors. But when we come to particles, I think the best way, I'm going to start out with universe zero, and we've got matter-free space. And we do, it's got electric permittivity and magnetic permeability. And I think we all know that that means if you've got a positive disturbance in one direction. You have an electric field disturbance in one direction. You have a magnetic field disturbance perpendicular to it. And this is highly schematic, of course. Positive making one cycle, magnetic field making one cycle. Of course, we all know conservation of principles. Positive field in this direction equals a negative field in this direction. A north magnetic pole in this direction is a south magnetic pole in this direction. So this you could consider it's a pictorial representation of a single wavelength, plane polarized photon under the Einstein de Broglie model. It's what they call psi, their wave function. And as Maxwell's equation said, this whole structure then moves at the speed of light, c, given by the square root of 1 over the square root of epsilon naught mu naught. Now, photons have mass. Einstein pointed that out in 1905 when he did his special relativity theory. Now, the photon's mass is in its electric and magnetic field. Now, in this particular case, the wave properties of a photon come from the wavy nature or sinusoidal nature of the fields. The particle property comes from its limited wavelength. This brings us to what we call Heisenberg's uncertainty principle. The photon is contained within this dimension. You can't define that accurately to a point, and that's essentially the physical origins of Heisenberg's uncertainty principle. The other thing is that in most photons, these two fields rotate through 360 degrees in one wavelength, and they become what is known as circularly polarized. I've tried here to indicate, using the arrow notation for strength, the situation of the positive field rotating through 3 wavelengths, basically 6 times. An indication here of all 4 fields sort of side on is not very clear. It becomes a little bit clearer here. And what happens is that if this whole structure twists through 180 degrees, or through 360 degrees per wavelength, then when it twists through 180 degrees, this is now on this side. And what you have is that all 4 fields, north and south magnetic pole and positive and negative electric charge, are all in particular quadrants. The thing about a north pole in this direction and a south pole in this direction, but a south pole pointing down means a north pole pointing up. So the magnetic fields become continuous. Now, for those interested, you can, this is the Einstein de Broglie wave function for a single wavelength circularly polarized photon. Other representations are possible. And the other thing to realize is because this has mass, the circularly polarized photon with the whole field turning through 360 degrees every wavelength, it gives a twist or spin, as we'll show later. It's measured at a value of h bar. So the other thing to bear in mind is space supports photons. So now for those who are maybe skeptical or prefer the standard model of a point particle, this is an image of a single photon that was taken by Romero, and she was part of a team. You'll see here the magnetic field is continuous, and the electric fields, well, I think we're all aware that if a positive field comes close to a negative field, they cancel each other out, and this gives the 2 black spots in the middle of the photon here. So I respectfully suggest that the model I'm using has a very good representation in physical reality. Now, how do we get from photons to particles? Well, it's been known for a long time that photons can generate particle-antiparticle pairs. At the same time, antiparticle annihilation generates photons. There's been long established a good relationship between photons and particles. Now I'm going to use a model that was first published by Williamson and van der Mark in 1997, and when they were applying it to electrons. And they literally said, and it was the fact that the photon, they proposed the electron was a photon making 2 revolutions per wavelength. And I'm suggesting that that is the universal model or universal structure of all particles. And I'll go through and show how it works. First, this is schematic illustration, quarter wavelength, half turn, half wavelength, full turn, right through to full wavelength, 2 turns. That gives the photon, the rotating photon, a radius of its wavelength divided by 4 pi. The other thing to note is that the photon ends touch, but they have no other reason to join. Now, to show its usefulness of this model, we'll use the fact that in 1925, Uhlenbeck and Goldschmidt discovered that electrons had a angular momentum of I omega equals half h bar. Now, in a hoop situation, I is mass times r squared, and omega is c over r, because the photon is at the axis of the photon is always traveling at c. That gives that mr squared times, if you then multiply both sides of I omega equals half h bar by omega equals c over r, it gives mr squared times c squared over r squared equals h over 4 pi, which is your half h bar, times 4 pi c over lambda, which is c over r. Cancelling out gives hc over lambda equals h nu equals e. If we go back to the original one and cross off the r squared, you get e equals mc squared. So in this situation, it just shows that energy is the photon traveling at c linearly. Mass is the same photon rotating twice per wavelength. It gives the mass of a particle is just as h nu over c squared, and its radius is h bar over 2mc. As the earlier slide showed, space supports photons, so its space also supports all particles made from rotating photons. Now, I'd like to show you, the first thing we should work out is how do these photons move? Well, there's two possibilities are that it sort of rolls along along its motion direction, and the other one is that it moves perpendicularly. So it rotates this way and then moves perpendicularly to it. Now, I'm only going to consider B because it has been verified by observation. Now, if we're to look at that, we're just considering the axis at this stage. Look at the axis of the photon. Viewed end on, it's just a circle. Viewed obliquely, this is stationary rotating photon, it will just look like an ellipse. And when viewed side on, it's just moving up and down. Now, when the photon particle moves, viewed end on, again, it's still just seen like a circle, but viewed obliquely, it'll be seen to spiral its way through. And finally, when you viewed side on, it will just be like a stretched string. Now, in all of these situations, the photon, or the axis of the photon, is traveling at c. Now, this makes it the hypotenuse of a right-angled triangle, and we can just apply Pythagoras' theorem. And I won't go through the full details. The math summaries are elsewhere, and I'll give them to you later. But one of the things I'd like to show, if you go through these, you finish up with the radial velocity equals the rest velocity times the square root of 1 minus v squared over c squared. The radius, a particle's radius does decrease with its speed. And it'll be shown later this has some very interesting consequences for particles. But it's only the radius that decreases, it's not the rest of space. The same calculations just give you the standard time, mass, and length corrections with increasing speed. Now, the other thing you should know that rotating photons are stable. Now, the spin of half h bar is angular momentum, and it's the whole mass rotating at the speed of light. It's a powerful gyroscope. On top of that, with charged particles, they have a h-bar twist or spin, which is also angular momentum. The conservation of angular momentum makes those particles very stable. And another reason for them being stable will be given a bit later. It should also point out in that derivation, the special relativity corrections apply only to particles. They do not apply to photons. Photons can only move at the speed of light, and whether it's traveling in a straight line or rotating, that axis is always at the speed of light. Now, as I said, in 1911, Einstein pointed out that photons had mass equals h nu over c squared. It has been measured many times. I'm at a loss why theoreticians keep ignoring it and try to pretend that they're massless particles. Now, just to illustrate a little bit more, here we have a situation, let's just consider it as a particle. It's made 6 revolutions, basically traveling 3 wavelengths. Because this is always traveling at the speed of light, if this represents, say, a low keV electron, this would be like many MeV. The centers of the oscillations are wide apart, and the diameter is quite small because essentially the length in both cases is the same. Now, I'd like to suggest that those last 3 slides show there is a unity between Einstein's special relativity corrections and the structure of matter. This structure automatically subjects all particles to the special relativity corrections. And it does also introduces that 4th correction of the reduction in radius as illustrated here with increased speed. And I respectfully suggest that helps to justify my earlier comment on photons rotating perpendicular to their travel direction. But what happens to the rest of the field? Well, if we consider circularly polarized photons, as I mentioned before, as was shown before, there will always be, each of the 4 fields will be in the one quadrant, in their own quadrant. So if you rotate it, say, in this direction, then in the first half cycle, you'll have the positive field on the outside, the negative field on the inside. The second half rotation, you'll still have the positive field on the outside. You'll have the south magnetic pole, in this case, pointing upwards in the first in the first half, and the north pole pointing southward in the second half. But the north pole pointing south is the same as the south pole pointing north, and that's what gives that the magnetic fields reinforce each other. And what you've got, when the photons are traveling linearly, the magnetic fields are open. When they are rotating twice per wavelength, the magnetic fields form a closed loop. I'll show you that a little bit more. And that closed loop, it gives extra stability to rotating circularly polarized photons than it does to rotating plane polarized photons. Now, if we have a look at a case of rotating plane polarized photons, then the polarities of the field swap. So it means in the first half of a plane polarized photon, we'll have, say, the positive field on the outside. In the second half, it'll have a negative field on the outside, so it will basically have no residual charge. The magnetic fields are in opposing directions. Therefore, they're not going to, if it's a Dirac particle, there will be no magnetic moment either. To visualize a rotating photon, we put an axis, say in this case, an axis off center, and if you just give that axis a twist, you'll get one field on the outside, the magnetic field pointing up, and the second field on the inside. And that gives you some indication what a particle would look like. Now, I'm going to give a how is charge generated? And I'm showing here, this is a charge, positively charged Dirac particle. That's a positron. You have the axis of rotation of the photon. You have the magnetic field surrounding it. But I've shown here that the electric field is in a plane. And this brings us to the origins of electric charge under this model. Now, the photon rotating at the speed of light at a very small diameter generates what we call a strong centripetal force. Secondary or virtual photons, you say, emitted or otherwise in the photons are the field particles of photons, and they're basically just thrown out. And they're virtual photons because if they don't interact with something else, they'll just be reabsorbed for conservation of mass purposes. Now, under QED theory, electric charge is caused by the emission and absorption of virtual photons. In this case, they will they'll be emitted at the plane or at the circumference of the rotating photon and in its plane. And its charge, the photons will spread out away from that plane as the photons, virtual, real, move away. So electric charge, in this model, electric charge is emitted at the circumference. It's a planar structure, so it is two-dimensional at its origin. Now, to some, this may seem a little different, but I'll show you later on. It has been observed to an accuracy of 0.01 FM, which in my thinking is reasonably accurate. Now, this origin shows up when, as I take an electron and positron annihilating each other. When they are rotating photons, they have opposite electric charge. They both have electric charge, even though it's opposite. When they unlock each other's angular momentum and become linear photons, their charge disappears. Yes, it can be postulated mathematically, but mathematics doesn't make things happen. Physics makes things happen. And that is the physical reason why it happens. Then we come to polarities of charge. Well, in this particular, you saw in the earlier couple of slides back that the electric field and the electric field is perpendicular to the magnetic field. And if you have a case, and I'm saying if you've got left-handed chirality, as shown here, the North Pole points out of the page, the photon rotates clockwise, and I'm using that as suggesting that that is negatively charged. On the other hand, right-handed polarity gives the North Pole pointing out. The photons rotates anti-clockwise, and I'm suggesting right-handed chirality gives positive charge. Now here we have 4 illustrations of what could be regarded as the same photon, photon with the same properties. Now there are only 2 ways it can rotate, clockwise, anti-clockwise or clockwise, and the spin of the photons can only spin one way or the other. So there are only a total of 4 combinations available. So here we see photon rotating anti-clockwise with the North Pole pointing out. Here we see the same photon rotating clockwise, and there the South Pole is pointing into the page. They are both positive charge, and with the south with the North Pole pointing out of the page and the photon rotating clockwise, you have a negative particle. And the same thing with the reverse, when the South Pole is pointing out, the North Pole is pointing in, the direction of the electron flow is anti-clockwise, and again, it will generate a negative charge. So that what you have is a situation where the two different rotation directions just define the spin of the particle. And here, if you look at A, you'll see that's a mirror image of D. You see they're both moving up that way in the middle, and both North Pole. They're mirror images of each other, and mirror images of each other makes them antiparticles. Now, it's been known for a long time that antiparticles are a mirror image of particles, and this is one of those reasons. Well, this is a physical reason. The different states of spin are determined purely by the direction which you look at it. I mean, a spin-up particle, if you use that as this case, is just an opposite side of the page image of a spin-down particle. No other spin or chirality states are possible. They are the only options you've got. I'd like to just show a brief statement on how this works. Consider we've got two observers. You've got a photon rotating clockwise. In zone A, both observers will see it rotating clockwise. In zone B, between the two observers, observer 1 would see it rotating anti-clockwise, while observer 2 will still see it rotating clockwise. And in zone 3, both observers will see it rotating anti-clockwise, even though it's continuing to rotate in the same direction. So just use that as just a further illustration that spin is just the other side of the page image of the same particle. That also brings us to a case of what happens when particles become entangled. Well, you take this situation when two electrons get close enough to become entangled, the only possibility you have is that the north pole of one is attracted to the south pole of the other, and they'll just stay that way. Now, the only way you can break that entanglement is to apply H bar twist to one of them. That turns the whole half H bar, goes from plus half H bar to minus half H bar. And that breaks, that's the only way you'll break the entanglement. And then they can go off you can let them go off as far as you like. And as long as you don't change the spins, then they'll always be, if they are entangled, they'll always be measured as having opposing spins. The other one of interest is the de Broglie wavelength. I mean, the thing about this particular model is that everything has a frequency. The energy of rest mass energy of a particle is m0c² equals h times its rest frequency. Its frequency at when it has energy EV, its frequency change from u0 to nu-v, and given by the relationship that EV² plus P² C² equals m0² c to the fourth. The Ke is Pc equals h nu Ke. You can just go directly from there to here. Pc equals hc over lambda Ke, gives lambda Ke equals h over p, which gives you the de Broglie wavelength. Now, while that's a mathematical description, which I said I would give the physics first, I'm just doing it in that way so you can hopefully understand what's happening physically a little bit better. Consider the case of an electron is just moving along through space. It's moving perpendicularly to its rotation is perpendicular to its direction of travel. And this shows rather crudely the fact that there will be a very high frequency oscillation which generated for an electron about 10 to the 20 hertz, which is fairly high. Now, for those who studied Feynman will know that high frequency electric field oscillations generate disturbances in the electric field. So the only disturbance that can be is electromagnetic. And the previous calculation showed, therefore, the only possible outcome. I suggest that what it is that the wave starts out as the influence of the oscillations disappear in either direction. The wave starts out weak, goes to a maximum where the particle is, and then diminishes back to nothing again. That particular wave, of course, is traveling at c, and it's just like any other electromagnetic wave. Now, to give you perhaps a bit of an appreciation, if the electron is moving slower, it has had longer to influence the field around it, so the wavelength, the influence will be greater and the wavelength will be longer. So just give a quick summary here of the properties that all particles will have that are constituted of, well, every individual particle consists of a photon making 2 revolutions per wavelength. That gives its mass, its radius, its Bohr magneton. Now this is, I haven't calculated this is measured. In E equals mc squared, energy is a linear photon, mass is the same photon rotating twice per wavelength. Particles are automatically subjected to special relativity corrections when they move. Space is, spin is angular momentum as first proposed, and that angular momentum is half h bar, and it is the mass of the photon making 2 revolutions per wavelength. There are only 2 states of spin possible. Both states exist at the same time. The direction from which they are viewed determines the measured value. All individual charged particles, the photon of all individual charged particles has an intrinsic spin or photon spin of h bar. Charge is generated at the rotating photon's circumferential axis basically because of its angular momentum. It is 2-dimensional in origin. The angular momentum is the same, and therefore charge will be the same for all particles. Neutral particles have a plus half and minus half charge. The magnetic field is perpendicular to that plane. Particle's charge is determined by the photon's rotation or chirality with respect to its magnetic field. An antiparticle is a mirror image of a particle. Different sides, different spins are just other sides of the page image of the same particle. As the particles move through space, their magnetic field leads, and they automatically generate the particle's de Broglie wavelength. Rotating photons have oscillating electric fields. That is the cause of the electron Zitterbewegung, and all other particles have equivalent oscillations. Now I'd like to briefly go through some of the particles. Now these are the standard well-known properties for an electron, but it has additional properties. The frequency of the oscillation is about 1 times 10 to the 20. It gives it a radius of 193 FM. And this is just a reverse of the positron shown earlier. You've got the electric field rotating in one direction, generating charge. You have the magnetic field, and the charge just spreads out from the axis as the photons get further away. Now, think about when this moves, the rotating axis will actually spiral its way through space. Now, that has led to what's called, some people call helical Mott scattering, where they believe they've detected the charge of an electron spiraling through space. Well, I respectfully suggest that that's just because that's what's happened when an electron moves. But electrons do have some awkward properties that have made them difficult to understand. The first, of course, they display nanometer dimensions at a few EV. As shown earlier, this is just the de Broglie wavelength. Near rest mass, with it's been known from other particles that magnetic moment is charge times radius. It's high EH by over 2mc suggests its radius is somewhat around this value. And yet at the same time, when it's accelerated to TeV energy, just has a scattering cross-section of about 10 to the minus 18 meters. So you've got a difference of 10 to the 9th in a particle detected structure. That's been difficult because that low scattering cross-section is just this special relativity corrections, as mentioned earlier. And I respectfully suggest that this rotating photon model explains them all and throws in the special relativity corrections and the royal wavelength for good measure. But I'll have some other awkward properties. One of them is interference. Well, fairly straightforward. You have two slits. The de Broglie wave is an electromagnetic wave. It will just pass through, and the waves will interfere as long as if there's no disturbance, the waves just interfere in the normal manner, and it really doesn't make any difference which slot the electron passes through. It'll gather in along the greater strength, and if you have enough of them, you'll get your interference pattern. But what happens when you try to measure through which slit the electron passes? Well, in order to do that, you have to place a sensor over one of them, which usually includes a voltage. Now, placing a voltage over one and not over another will put the phases of the same electromagnetic wave, will just put them out of phase. You won't get an interference pattern. If you put voltages on both of them that are exactly the same, you will, while the waves may be the same, by the time the electron goes through one of them, it will disturb the waves through the one through which it passes. So again, you won't get an interference pattern. Another one, of course, is tunneling. And the well-known effect is that you have an electron approaching a barrier. It hasn't got enough energy to overcome it. Its de Broglie wave can be long enough that it can appear on the other side. You have the possibility, the electron can appear anywhere on that wave, according to the standard theory, and therefore it has a possibility of being able to penetrate or tunnel through. But there's possibly a particle explanation. And this is just referred to the good old billiard ball trick where you set up a group of billiard balls. One comes along, it hits, transfers momentum all the way through, and the end billiard ball drops out. Well, electrons are in a complex taut field, and they're attracted by protons, repelled by other electrons. They basically respond to every stimulus. So you have an electron coming along that will hit into a target and transfer momentum through the barrier. And if at the end an electron has sufficient energy to overcome the work function between the two surfaces, it'll pop out the other end. Now, I suggest that there is a way of distinguishing between the two, that lower energy electrons have longer wavelength and therefore greater probability of tunneling, and higher electrons have larger momentum, and that would give them greater probability of an electron emerging out the other end. I don't think that's a very difficult experiment to try. Next, we come to photons. They've got all of these, the usual list of properties, charge, but the magnetic moment is beyond the charge times radius situation. Its frequencies are these values times 10 to the 23 hertz, and its radius is 0.1052 FM. Now, we're in the fortunate position that the charge distribution on photons has been measured and was done by Hofstadter and his team in the 50s. If all of the charge was was at this dimension, then it would have this magnetic moment, and you would have all of the charge at this point, which is very close to 0.1052 FM. If it was measured experimentally, you call it experimental limitations would mean you wouldn't measure it as a single point. You'll get a bit of an exponential decay. It's shown there. What is actually measured is this curve 2. It peaks, yes, about 0.105, just about 0.1 FM. Now, I suggest that that is a very good indication that charge is generated, or the charge generated by this mechanism has been detected to an accuracy of about 0.01 FM, because it's pretty close to, within 1/10 of that distance. Curve 3 is just part of the way between these two. It really doesn't mean anything. But the important thing out of this is that there is something within a proton that's spreading its charge. Instead of being here, it's spread out here, and it's increasing its magnetic moment. So we now investigate what that could be. Well, there's a couple of possibilities. One is that the wavelength, which is the black one here, the wavelength is non-sinusoidal. Now, the black curve is just a sine wave. The blue curve is if it had a 1/3 frequency harmonic imposed upon it, then it would get the red curve. Now, why 1/3 frequency harmonics? Well, this is a plot in what you would call a momentum space. Whenever there's a regular disturbance, a 1/3 frequency, where the disturbance drops that down, the 1/3 frequency goes up. And anybody who's ever talked to radio engineers knows that getting rid of 1/3 frequency harmonics is a real problem with radio waves. Now, if that is made to rotate, what you'll get the main oscillation, and then you'll get an oscillation of 1/3 of the frequency, which will be 3 times the wavelength. Now, the other possibility is that the centripetal force on a proton, it's huge. I mean, it's the whole mass of the proton, which is nearly 2,000 times that of the electron, rotating in a radius about 1/2000th that of the electron. And it's just, everything goes everywhere. What will happen is that then you'll get these very large photons massive photons being thrown off, and they will have the 1/3 frequency harmonics. So this is just gives a situation where you have the main 1/3 main, what I call a P/1 oscillation, has generated 3 P/3 oscillations. Its spin is conserved, mass is conserved, but they're all positive. So charge isn't conserved. So with the equal probability of that occurring, you would have the probability of 2 negative charges and 1 positive charge, which would then give you a total out of the 6. You would have 4 positive and 2 negative, which gives you an average of 2 positive P/3 oscillations and 1 negative P/3 oscillation. Now, here's just a quick indication of the different properties of the primary P/3 and P/9. The thing about P/9, as the frequency diminishes, the radius increases, the magnetic moment increases. One's worth having a quick look at here is the mass of a p/9 oscillation, 104.25. 105.6, not much different. More on that later. These are the proportions that you need to finish up getting the proton's observed magnetic moment and charge distribution. So it is suggested that these harmonics are actually spreading out your charge and increasing the magnetic moment. Now, these oscillations will just pop into and out of existence as required for conservation principles. And while this may seem a little different, they have all been detected. And so let's take the p/1, 0.105 FM. That looks like a pretty good detection there. The p/3, 2 positive, 1 negative, near the proton center. That remind anybody of something? Quarks, perhaps? Or are they quarks? Or are they just 1/3 rotating harmonics? And the p/9, well, yes, it's, as I'll show you later on, it's got almost exactly the same properties as a muon. The only difference is that in the proton, it's bound, so its mass is just a little bit less than when it's free. Here's a few ways of representing a proton. Here we have just a plan view of the charge. The rings just merely indicate the intensity of the charge as best I can. This one you've seen. This one is just that doubled up because its charge is distributed all around. Here it's like an oblique view of the distribution of charge. Its height is charge, not physical position. This one, as the previous ones, where it just shows the whole thing is embedded in a positive field. And here you have this charge plane viewed obliquely and a magnetic field surrounding it. The whole thing to note about this is everything is electromagnetic. Nothing is solid mass. If we come to neutrons, again, the same sort of properties you're already familiar with. Think about it, it's zero charge, but it has a negative magnetic moment. And the properties of the rotating photon are pretty much the same as that of a proton. This shows the charge distribution of the neutron. It starts out positive, which I'll show here is the positive core. It then goes negative, and for the same reason that the proton had 2 positive and 1 negative, the neutron, because this oscillation is negative, will have 2 negative and 1 positive. It then goes positive, which are these p/3 oscillation, p/9 oscillations, which are the same as a proton. But in order to match this very high magnetic moment, you need the n/27 oscillations. Now, here's a table. This just shows the properties of the various harmonics. The n/1 is positive, n/3 is negative, n/9 positive, n/27 negative. And these are the proportions that are needed, and that finishes up to match the neutron's observed magnetic moment and charge distribution. One thing that's worth looking at is the mass of the n/27 oscillation. 34.8, and the bound muon 104.4. 109 MeV per c squared is looking pretty good, isn't it? Again, here are various representations of the neutron. Its oblique charge, and the one I like, the positive central core, negative p/3, negative n/3, positive n/9 oscillations, and finally very large negative n/3. Next, we come to a neutrino. Usual property, organic properties, spin half h bar, no charge, no magnetic moment, and an upper mass of 0.1 eV per c squared. Here I've just done a schematic illustration. A neutron decays to a proton plus an electron plus. You've got charge 0 going to plus E, minus E. Spin goes from plus h bar, gives plus h bar, which is 1 h bar too many. And therefore you have to have a spin minus half h bar. All other things are conserved. The standard model treats neutrinos as point particles with properties attached. Under this model, a neutrino is a Dirac particle composed of a rotating plane polarized photons. And when neutrons decay to protons, it's just a rearrangement of electromagnetic oscillations with all factors conserved. I mean, not like in the standard model. How do quarks and gluons decay to give an electron and a muon when the quarks are supposed to be elementary particles? This one's just straightforward. But you see a mass of 10 to the minus eV per c squared. Why is it so small? Well, you've got three possibilities. The time when a neutron, neutrons have a half-life is what, 12, 15 minutes, somewhere around there. But by the time it actually starts to decay, the decay process gives it a rest mass, it takes place in about 10 to the minus 10 seconds. That gives it a rest mass of approximately 10 to the minus 4 eV per c squared. Also, the time for a neutrino to arrive after photons from supernova, again, they're within a few seconds. Now, if we do the reverse of the corrections, relativistic velocity corrections, you get that mv over m naught squared. In order to travel tens of thousands of light years and be just a short time behind a photon, you need that rest mass of about 10 to the minus 4 eV per c squared. And then finally have these results by Bernardini, which suggests that the maximum flux of neutrinos is again about that 10 to the minus 3, so about 10 to the minus 4 eV per c squared. So it just suggests that all of those put together, yes, the photon, but the neutrino has a rest mass of about 10 to the minus 4 eV per c squared. Now to have a quick look at what that means. First of all, cosmological neutrinos, a wavelength of about 20 millimeters and a radius roughly of 2 millimeters. And that is why their large radius is why their small mass can still have half h bar angular momentum. Now, the neutrino radius of 2 millimeters makes them by far the universe's strongest gyroscope. I mean, it's very difficult. They just travel. It's very difficult for them to change their direction of travel. They can only be absorbed when if their leading structure strikes a receptive nucleus in exactly the right position. I mean, electrons have no way they can absorb a neutrino. A 0.01 eV neutrino has a speed of about 0.99 c. And that's why 0.01 EV is a very low energy neutrino, but that is why neutrinos are all detected as traveling basically at the speed of light. The rest mass gives them a temperature of about 1.7, or temperature equivalent, about 1.7 degrees K. So that although rotating plane polarized photons are not stable, there's just no lower energy to which the neutrino can decay. That's what it is. Another particular property, a neutrino radius decreases with increasing energy, just the same as I showed earlier. A 1 GeV neutrino has about the same radius as a nucleon's central core. And that's why higher energy neutrinos are easier to detect, because they're about the same size as the neutrons that can, as the nucleons and nuclei that can detect them. So I respectfully suggest that under this rotating photon model, neutrons are not difficult to understand. They're low frequency, or they're low mass, high angular momentum for mass, zero charge, zero magnetic moment, just really make them difficult to stop. Now we come to elementary particles. Now, the first thing to realize about elementary particles is Einstein's special relativity corrections. Mass increases and time slows down when particles travel at a high speed. And they're quite stable at that. I mean, GeV cosmic rays travel for tens of thousands of years without decaying. But when they stop, they have excess mass for their new rest time. They've got to get rid of it. Now they can do that by emitting linear photons, which we all know as Bremsstrahlung. And the other thing is that these outer P/9 oscillations can just be jolted out. And here I'm just showing that their properties are just the same as a muon. As I said, their muon's mass is a bit higher because inside the nucleus, the particles are bound, so they lose a bit of their mass to that binding out, and they pick that up when they're free. But when you jolt a positive muon out of a proton, it converts it to a neutron. Now, as we know, when a proton decays to a neutron, it generates an N/27 oscillation, and that has a mass about 34.8 MeV. So combining the 105.6 with 138, you get with 34, you get about 139 MeV per c squared. Now, and then 27 oscillations can be negative, neutral, and positive. I mean, you've got to have everything going on when the atoms collide, when the nucleons collide with each other at very high energies. If a neutral 27 attaches itself to a charged muon, there's not much binding energy there, so the mass stays at around about 139 MeV per c squared. It has spin 0 or 1, and it decays to a muon plus whatever else. But when you have opposite charges, you have a positive attaching to a negative. It will give some binding energy. That drops the mass from 139 MeV to about 135 MeV per c squared. And the similar dimensions means that the two, the radii only differs by a factor of 3, so the two can actually sometimes release each other's angular momentum, in which case they will decay to photons as well as decaying to muons, as shown here. So because pions are by far the most common particles emitted in proton collisions. And in energetic protons, they just keep replacing the lost oscillations until they reach a stable state. Now, in doing that, all they do is just cascade through a series of quasi-stable particles emitting pions and photons as appropriate until they reach a stable nucleus rest mass, stable nucleon rest mass. I won't pronounce these particles, but these are just the final stages of decay. This particle generates that plus a pion, this one, that plus a pion, a neutron plus a pion, and they're all generating pions. And what I respectfully suggest, these are not separate particles. They are simply the final stages of nucleons cascading to a stable rest state. The situation with higher energy nucleons is more complex, but not fundamentally different. Higher energy particles can form more combinations with greater complexity, making them more difficult to understand. But are they really anything more than just adding mass to nucleons, the removal of which gives structures that aren't present in them at rest? Well, if there is something more, it should show up in the way nucleons bind to form nuclei. So I'll now give you a quick introduction to that. Just as a reminder, here are what the representations of the nucleons that I'll use: proton and neutron. Explained those before. Again, these circles just represent intensity of charge, not rotating photons. So what happens when a proton comes close to a neutron? Well, here we've got two situations, one of 5 FM spacing and one of 2.5 FM. The first thing to note, because charge is generated in a plane, they will align themselves in a planar array. Here at 5 FM, you'll see there's just a tiny bit of overlap of the neutrons n/27 with the protons p/9. There will be, if their spins are the same, there will be a bit of a magnetic loop between them. But at 5 FM separation, there isn't enough overlap to give any form of binding. However, the situation changes. At 2.5 FM, I mean, the magnetic binding is virtually R-cubed, so the magnetic binding will be about eight times that at this distance, and you're starting to get some of the protons p/9 overlapping the neutrons n/3. That will give a particle with 2h bar. It'll have spin +1 because they're both spinning in the same direction, and its magnetic moment will be the difference between the two. So that suggests that there is some magnetic binding when the charges overlap. So what I want to do now is just take you through the different stages as the protons, or as the neutron gets closer to a proton. Now, 3 FM, so there's not much overlapping, but you see here at 2.5 FM, there is starting to be significant overlap between the p/9 and the neutrons (n/3). Now, overlap means that charges, because they're rotating photons, they're overlapping. They are overlapping at essentially zero distance. And you can consider this sort of binding division by zero electric attraction. I mean, after all, plus 0.1 E overlapping at minus 0.1 E at 0.1 FM has the same force as a plus E overlapping a minus E, or close to a minus E, separated by 1 FM. So it is a strong force. The shorter distance also increases magnetic binding. And the closer you get, of course, the more the overlap, the stronger the binding, until you get to about 1.2 FM. That's about as strong as it gets. And now you've got the two charges starting to overlap, two positive charges starting to overlap. By 1 FM, it's quite a strong overlap. At 0.5 FM, it's a huge overlap. I respectfully suggest that shows up in this work by Cook. It shows the relative binding strength versus distance, and starting out 3, 4, 3, 2, about 1.2 is about the strongest, and suddenly it becomes very, very strongly repulsive. And I suggest that's the reason why. Next, we have a quick look at what happens with neutrons at different center-to-center spacings. Really, a bit of binding, perhaps, maybe, until you get to about 1 FM. And then negative n/3 oscillations are really strongly overlapping each other, and that's why you really can't get neutrons much closer to each other than about 1 FM. Now, to give an indication of how this works, here we'll consider these A equals 3. The two, in the first case, you have 3H or tritium. Two nucleons have opposing spins so that they will add to magnetic binding. They both, there's a tiny bit of overlap of the P/9 with the N/3, but not much. These two can, well, there's no repulsion between the neutrons, so they can move in close to the proton, and that well, first of all, because the neutrons are reverse spin, the residual magnetic moment will be very close to that of a proton, and it'll have a spin half. Because there's no repulsion to the neutrons, they can move a little bit closer, so the proton to neutron binding energy is, well, it's been measured, 4.2, total binding energy divided by 2, 4.24 MeV average. The separation centered about 1.6 FM. We now go to 3H, 3He. The two protons have different spins so that they can get some magnetic binding to each other. One of them is bound to the neutron. One of them will have some magnetic binding, the other one won't. The protons will try to push each other far away apart, and that's why the distances are a bit further apart, and they have a slightly weaker binding energy per proton-neutron bond. And they will have these spins cancel out, so they'll have again a residual spin of half H bar, and their magnetic moment will essentially be that of the residual neutron, which is of course what is observed. Going to 4He alpha particle. The protons, this shows all the fields imposed upon each other. The protons will try and get as far away from each other as possible, and the neutrons will be drawn in as much as possible. Like this may be hidden by, but what you will have is that the spins of the equivalent, proton will have one proton spin up, the other one spin down, one neutron spin up, one neutron spin down to get maximum magnetic binding. To finish up with a particle, no magnetic binding, and 28.28 EV binding energy. It's a very they're very strongly bound, 7.07 MeV per c squared at a distance of about 1.2 FM. What we can now do, we've got several points that we know, and we just plot these in terms of binding energy that way in MeV versus proton to neutron center to center distances here. That's 4He, tritium, 3He, deuteron, and the overlap between the N26 oscillations and the protons, neutrons N/26 and the protons P/3, it stops at around about 5.5, 6, somewhere around there. I'm not exactly sure when. But that's the reason why the strong nuclear force ends about there. The other reason, why can't a helium, why can't we have a equals 5? Well, the proton can immerse itself in neutrons, one of the neutrons, N/27, but they don't last very long, so it won't stay there. And the same thing, a neutron can put its N27 over one of the protons, but they don't last very long. So A equals 5 nucleons are not stable. Okay, now to go through some nuclear binding rules. I'm not going to read these out to you. I just like to show you they exist and they're not very complicated. But to show them, you have consider the possibilities of lithium nuclei. You have two possibilities. You have an alpha particle with a deuteron superimposed on it. Well, the only other possibility is the three protons as far away from each other as possible and held together by the neutrons. So it's hidden behind here, but there's an Li7. It's just putting a neutron in there. The Li7 is actually the largest nucleus that can form in a single layer. I mean, you can tell the difference between these. If it was this structure, the density, the charge density of a lithium nucleus would be similar to that of an alpha particle. If not, the alpha particle's got the strongest charge density, and lithium has the weakest charge density because that's one where the protons are furthest apart. The other one to look at, carbon nucleus. As has been proposed that there could be three alpha particles somehow joined. Yes, it could be that with the appropriate alignment of magnetic fields, but that would give the two things. It doesn't give anywhere for carbon to have any isotopes, and it would also make the carbon a very strong charge density. So the only other possibility is two of these equilateral triangular states superimposed upon each other. Now, a few years ago, experimentalists are pretty good, and they did these measurements and they found out that yes, indeed, the structure of a carbon nucleus was an equilateral prism structure. So this structure has been observed. So I guess we're on the right track to showing that this model does work. Just like to quickly go through, there are a lot of higher atomic number nuclei which we need to consider as well, and under the rules of binding, these are the structures that can form in a particular layer. First thing to note, they are not circular. Second thing to note, two protons, 2 neutrons, 6 protons, 9 neutrons, 9 protons, 14 neutrons, 17 protons, 27 neutrons. You need, in order to fit in this structure, you need more neutrons. As the number of protons increases, you need more neutrons to bind them. The other thing to note, if you have a look at each one of these nucleons is in at least one alpha particle structure. And that's why it's so easy to knock alpha particles out of nuclei by giving them a bit of a hit with something. These are some of the, not all of these neutron lattice positions have to be filled all the time. And these are some of the layer structures that exist when neutron vacancies exist. The binding between, within a layer, you have that strong electric and magnetic binding that I mentioned earlier. But binding between layers is just a result of the residual magnetic field. Now, one thing about these two structures is that most nuclei, as long as they're assembled according to, most nuclei that are assembled with using these structures are either stable or will have a half-life of a few seconds. We'll get more into that later. To give you an indication of just this at work, here between 24 AL and 30 AL, you have the limits of isotopes under this structure, and you'll see the lowest number 2 seconds, the highest number 3 seconds. The most abundant isotope, Al27, has one of its neutron lattice vacancy positions filled. And the reason for that is that an even number of neutrons gives stronger binding than an odd number of neutrons, just because there's one extra loop formed. Again, if you just add, add protons, add neutrons, yes, well, I can't see it. You add neutrons and you get unstable, because a neutron can attach itself by its N27 to any external proton, but because the oscillation doesn't last that long, it's not a very stable bonding. Here again, showing removing one neutron below that one second neutron, the half-lives diminish. And showing here where some neutrons have been attached to some protons, as mentioned earlier, half-life is quite low. Now, for those who are really keen, what you can do is you can work out the spins, the orientations that are required to get maximum magnetic binding. Then you finish up, when you do that, you'll find that you have a spin of 2.5 or 5/2. If you add up the magnetic moments, you should get a value of 4.55 mu BP, but it's actually been measured at 3.64. The difference is just due to a slight compression of rotating photons during their overlap process. But otherwise, that's all. I want to just show you quickly oxygen, and just a couple of other examples. You have oxygen. It's the most abundant isotope, has 2 He there, and these two neutron lattice positions are not filled. The rest of it, again, you can attach protons to, you can attach neutrons to external protons, but the more you attach, the smaller, the shorter the half-life. Calcium is an interesting one. 2 reasons. First of all, it's the most abundant isotope, has all of its neutron lattice positions vacant in this 6-layered structure. And there we go through, as you go up, it's the low, that's just like oxygen has, calcium has, and that's all of the even Z numbers above 6 and above are in that position. But when you get to 48 Ca, which is still a stable isotope, you've filled in this position, you've filled all of the neutron lattice vacancies at 46. So the only way that this can be stable is that you have to have a rearrangement of the number of layers in the nucleus. And in this case, calcium 40 has 4 layers, not the 6 layers of the previous ones. Now, the reason I mention this is that when you get to higher Z, around 40, 50, 60, and that sort of thing, you can get many different isotopes. The same isotope of a particular element can have different structures, and it is the structure that determines the stability of the nucleus. And basically, if you have the strong nuclear binding consists of overlapping charges which appear and disappear. Well, if the arrangements of overlapping charges are different, then some can disappear faster than others. And that's the reason why you have at higher Zs, you can have the 2 isotopes having the 1 isotope having 2 different half-lives. Anyway, let's move on. What I want to show you, one of the problems that bothered nuclear physicists for a long time is what's called the nuclear skin effect. Now it's shown here, I'll show it here with, let's just say, gold and bismuth. The charge diminishes it's a distance of the charge diminishes from 90%, which in these two cases is about 5.5 FM, to about 10%, which is around about 2 FM. So that's about 2.5 FM. Now, if you have a look at this curve here, you will see that, yes, starting out 0.1, it's still dropping at about at 2 FM, allowing that these nuclei are pseudo-spherical so that you will get some charge diminution. And they're not cylinders, they have a bit of a curved shape, and allowing for that curved shape. What you're doing is measuring this charge distribution, and that goes along with what I said very early on when I derived the special relativity corrections. The nucleus, or all nucleons, in fact, all particles move with their the charge plane rotating in this direction. They move in this direction. So what you're seeing here in this skin effect is all of these charges superimposed upon each other, and the electrons coming down from the top scattering from them. So the skin effect really just shows that, yes, nucleons, or all particles, when they move, orient their spins so that they present the charge plane in perpendicular. The charge plane is perpendicular to their direction of motion. Another one that's perhaps worth a quick look at, I'll show here, carbon and oxygen. You'll find there that they go to a maximum and then they just dip down a bit. Now, if you have a look here at the carbon structure, you've got 3, because remember, it has an equilateral, prism equilateral triangular shape. You have these 2 layers on top of each other, all the charges on the outside. So electrons coming down scatter mostly on the outside and somewhat less on the inside. Oxygen is exactly the same thing. But there you have 3 layers with charges on the outside and virtually nothing in the middle. Electrons scattering out of oxygen can come back from 3 layers. So that depth drops off a bit. I respectfully suggest that this is strong proof of the correctness of the model, but the charges, the particles do move always with their charge plane, shown here, perpendicular to their motion direction. Helium has the very, very high core density, because this is as close as you can get. It's the only 2 proton structure where both protons are pulled in quite strongly. Just like to prickly measure, I mentioned something about lead. PB82, it's got all of its neutron lattice positions vacant, and all its stable isotopes are lower mass. Excluding PB209, which is also stable if you regard, stable. All other nuclei with higher Z first of all, they'll have the most stable one will have all of the most abundant one. Because of this, you won't find any higher. You won't find any higher atomic number or mass number isotope than these that are stable. There's no such thing as magic numbers. As I mentioned before, neutrons can attach to external protons. But by the time there's about 10 of them in most cases, the half-life became really short. And there has been attempts to determine the neutron drip line by smashing larger nuclei together and measuring what comes out. But In order for to get the high number they give with sodium, you do need a bit of magnetic binding only, and those isotopes are very, very short-lived. And they're doing that so they can learn something about the structure of nuclei. And I respectfully suggest that if they use this model, they'll get a lot further than they will with the way they're currently heading. Just as a quick one, the two dotted lines represent the limits of which the most abundant and stable nuclei with half-lives above seconds or two are found. And you can, they've got thousands of nuclei, and this works exceedingly well with just a tiny bit up here where it goes outside, and I haven't modified the theory yet. The other thing is the most abundant nuclei start out at less than 20 at the minimum A for Z. It reaches a maximum A for Z. It's certainly there by 82. I don't know exactly when it gets there. The most stable isotopes gradually change from one to the other. And when you get to tin, it's about 52. It's not quite in the middle of this, but it's got the most number of isotopes, with the less abundant ones on the lower, or sorry, more isotopes. There's 50 more isotopes below the most abundant line than above it. I'd like to very, very briefly go on to, because of the interest in uranium, it's U90, 238, again, all neutron lattice positions filled, 235, I've got neutron vacancies, as you would expect. The interest of the uranium is in fission, so I just want to show you quickly what's happening there. This is the same U235 as shown before. It's an 8-layered structure. So you've got the middle down here. The line H, that is where a fracture plane only has to break 4 proton to neutron bonds in this situation. So if it fissions, if it splits along that line and this layer attaches to the upper layer, it'll give an atomic number, minding I haven't taken off the extra neutrons, but it'll give an atomic number of 134, and the bottom one will be left with an atomic number of 101. If we go and have a look at, these are the mass number of fission fragments and presented by Weil. 101 near the top, 134 pretty close to near the top. The chances of splitting, but if for example, we just split off here, this little section here, and it went with the bottom and the remainder stayed with the top, you would get, the top one would have 161 and the bottom one would have 74. And you show here 74, yeah, not bad. 161, well, we've got to take off a neutron or two. You can take them off whenever you like, but I respectfully suggest that this particular model is rather good at also explaining what is happening with uranium's fission. Now, just briefly run through models with when nucleons bind. First of all, they completely retain their structural integrity. There's no quark, gluon soup or anything like that. The strong force is a combination of the opposing charges overlapping at essentially zero distance and the magnetic fields oriented to give maximum magnetic binding. Nuclei with Z greater than 3 all form in multiple layers. The layers are held together by the residual magnetic field, and it's probably less than, it's around about 20% or less than the binding per nucleon in the within each plane. So the neutrons required to hold photons together increases faster at a rate that in this lattice. Allows us 208 and 209 PB and BI respectively are the highest A and Z stable nuclei. You can search as much as you can get funds for, but you will not find any higher magic number nuclei that are stable. This model allows the structure and some properties of any nucleus of any A and Z to be calculated to either match observed properties or predict new ones if you're looking for them. The nuclear skin effect is just due to the way the proton's charge distribution is being measured because of the way they move. They always move exposing their spread out charge. The spin of a nucleus is the sum of the individual nucleons. Nuclei do not spin. The magnetic moment of a nucleus is the sum of the moments of the individual nucleons with a slight rotation, slight rotating photon distortion, just because the charges overlap. The transient nature of the rotating photon harmonics, in that they pop into and out of existence, means that the strong force periodically fails. That depends upon the structure, and then radioactive decay follows as just the harmonics are rearranged. I respectfully suggest that this model's success in matching nuclear structures and properties leaves little room for further modification by a better understanding of the 200 plus elementary particles that have been detected, muons and pions excluded. But just to finish off, you can't really start building the universe around you until such time as you put electrons around nuclei. I mean, the standard model was that, classical physics, the electron spirals around, emits photons as it does to change direction, spirals into the nucleus, and the latest calculation suggested that would be happening in about 10 to the minus 12 seconds. It doesn't happen. So in order to overcome that, it was postulated that orbits are quantized. And they were quantized, depending on which books you read. Fixed orbits follow fixed de Broglie wavelengths or integers of angular momentum. The orbits don't include the nucleus, and because they're fixed, they don't have to emit photons to change their direction. The nucleus won't collapse, problem solved. Yes, well, maybe. But the reality, under this model, electrons are larger. The diameter of a rest, an electron at rest, is 386 FM. That of even the largest uranium nucleus is only about 20 FM. I mean, it just won't fit. You can't put it there. And even if you could, naturally occurring don't have any gap to accept them, so atoms won't collapse. But that doesn't answer why electrons have fixed binding energies, and which have been interpreted as quantized orbits. Well, obviously the 1s1 orbit binding energy is really well fixed. It's Rydberg's equation, and there's the calculated values, the measured values, 122.45, yeah, not so bad. So when 306.1, it starts to get a bit worse as you go down as the atomic number increases, but otherwise not so bad. But what about the 1s2 electron? Well, the first thing to realize is there is only a fixed number of protons within a nucleus, and each electron that's in there, say the 1s1 electron, screens out the effect of one proton. So the binding energy of a 1s2 electron is basically the 1s1 electron minus some function of screening. Well, I suggest that this is one equation that is a screening, just one screening equation. If you haven't worked out, all values are expressed in electron volts. I'm a physicist, not a chemist. I don't understand kcals per mole very well. Anyway, unfortunately, the table is a bit hidden, but these are the calculated. We see here 7478, 7481, 648, 6847, 6851. The binding energies due to this screening function are quite closely match what has been observed. Now, doing it just for one is not good, so I've done it for 2s1, 2s2, 2p1, 2p2 as well. And again, the same. Here are some suitable equations. The calculated values, which are in the normal print, are calculated from the experimentally measured values, which were the previous lot. And go through again, 190.4, 185, 618.8, 611.2. 1571, 1570. Yeah, it's reasonable. It's a little bit better than what was obtained from the Rydberg constant, Rydberg equation by the time you got down to here. Same thing with 2s1, 2s2, 400, 398, 1218, 1213, 1634. I'm saying they've done the same 2p1, 211, 208, 480, 479, 754, 756, and so on, including the 2p2 ones, 1250, 1260, 1392. So all I'm suggesting out of this is that the orbits are not quantized because of the Broglie wavelength or angular momentum. It's just that there are a fixed number of protons in a nucleus, inner screen out but it doesn't answer, there's still other questions to be answered. And one of them is, or a couple of them, so how do electrons move in atoms, and why do they pair? Well, they don't move, they certainly don't move in neat orbits. This model supports a suggestion made by Berry a couple of decades ago. They move more like pairs of electrons subject to some restriction. In their motion, they can just traverse across an atom about 10 to the 14 to 10 to the 16 times per second. They exchange photons with the nucleus to keep within the nuclear potential well, and they move with fixed binding energies and not in fixed orbits. That, as far as spectroscopy is concerned, there's no difference. But it does make some difference to how, well, we don't have to postulate anything to get these orbits, apart from the screening effect, which I think is obvious. There are other conservation rules. The other one is, why do electrons pair? Well, their angular momentum of half h bar is the whole mass rotating at the speed of light in a radius hundreds of times larger than that of a proton. They're a powerful gyroscope, and just like any other gyroscope, they need to exchange angular momentum with something. And that is done, they just exchange photons, and their rotating photon structure means they're continually emitting and absorbing photons that generate electric charge. So electrons just pair so that they can move freely. So now electron pairing between different atoms, as we know, is the foundation of chemical bonding and molecular structure, and what enables us to build the universe, what enables us, or what is responsible for the world we see around us. But another thing, we come to bond angles or bonds. Now, we just consider, I think we all know that carbon has tetrahedral bonding. All their four bonds are as far away from each other as they can possibly get. And all that happens is that each, in the case of methane, you have one electron from a hydrogen atom and one from a carbon are bonded and forms a pair of electrons. These pairs get as far away from each other as possible, and that's what gives rise. And That's what gives the tetrahedral structure. All of the bonds between all of the four angles on methane and on carbon generally are as far away from each other as possible. On the other hand, nitrogen has three electrons that can bond, and then when they bond, sorry, nitrogen has, and when they bond one each with hydrogen, these angles are as far away from each other as possible, but you have two electrons on the top that are unbound. Well, they're bound to each other, but the charge that they generate just pushes these angles down a little bit. With oxygen, you have just two electrons will pair with two atoms, two electrons from, say, hydrogen. The bonds will be as far away from each other as possible, so they're 180-degree opposite. You have four electrons on the top, and those four then push the bond angles down. I think these are pushed down by about 10 degrees. These are pushed down by about 30, 35 degrees, somewhere around there. But the angles of other molecules just depend upon local structure and residual electrons. I'll just leave that for chemists to study, but I'd just like to give you an indication of this is how it can happen. Look, I know other explanations are possible, but this is also equally valid in my opinion, because it comes fixed with all of the other things like special relativity, corrections, and so forth. Now, just as a brief conclusion, this has been a brief introduction to rotating photon particle physics. It's a discrete particle theory. It uses three space dimensions and time, known particles, physical principles, and constants. Respectfully suggested unifies electromagnetism with the fundamental structure of matter particles, with Einstein's special relativity corrections, the Royal wavelength, the origins of charge, elementary particles, the strong nuclear force and nuclear structure with atoms and the origins of their chemical properties. It's matched many observations and made many testable predictions. It's answered many questions that eluded nuclear physicists for decades. What is nuclear binding? The reason for its short range, the structure of nuclei, the nuclei skin effect, and more. I mean, it's been a physical description. It's done without complex maths. Pythagoras' theorem, as I said, gives special relativity corrections as well as the de Broglie wavelength. Much of the rest of the maths is available elsewhere. I'll get onto that in a minute. I'd just like to, I think we've all been known, people have been searching for, been using field theories, and some suggest that particles are just manifestations in a field. I respectively suggest that particles generate the fields, but in the searching for quantum field theory, unified field theory, a grand unified theory of everything has been difficult, and progress has been slow, if it can be called progress. I'd just like to suggest that perhaps time to try a unified particle and field theory. Starting out with a field theory, as I mentioned before, a photon is an electromagnetic field. If you get it rotating twice per wavelength, you get the particle. So you can start with a field theory and generate the particles and turn the fields. And I think that would, personally think that's a better way of working. I'd just like to leave you with a little bit of something. There are those who have the sort of not invented here syndrome. I'd just like to mention this physical study has been extended to include the properties of nuclei that alter a property of free space. The radial differential of that property gives gravity. Newton's inverse square law is the first approximation. Einstein's field equations is the second approximation. The exact solution predicts the torus shape that has been imaged in galaxy centers. It and many other answers that you may have can be found in this book. Further details on aspects of what I presented, you can go to the Quicycle website. Now, I suggest that I've outlined there the properties of all known stable particles, how they combine to shape matter, and given the briefest introduction to gravity, I'm going to leave you with, just to indicate, this gives all a table of contents of the book. It gives you all of the topics that I have written on. It's been very extensive. Not much has been published because I found out a long time ago, reviewers don't like non-standard model presentations. This is not standard model. I just decided to finish the study before taking too much, but I will acknowledge, yes, the UK Institute of Physics was good enough to publish that paper on the physics of Einstein's gravity. Thank you.